The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome. Thanks for joining us for another webinar in our continuing AMS webinar series that we run every month. Today's topic for the webinar is Advanced 3-Axis Machining. My name is Joe Anand, and I'm the product manager here at MecSoft. I will be joined today by Uday Honalagore, our support manager, who's actually going to be doing the demonstration. This webinar, as usual, is part of the webinar series that we run every month. We call that the AMS webinar series. And if you're attending this, you're either subscribed to our AMS program, which is the annual maintenance service program, or you've actually bought access to it. So if you haven't subscribed to the service, I would highly urge you to add that subscription, because not only do you get upgrades, automatic upgrades, but you also get the important information webinars like these every month. Once this webinar is completed, we will make the recording available to everybody and then send it out in a day or two. And but before we get started, we want to keep this webinar as interactive as possible. So a few housekeeping tips. You use your questions window for questions during the webinar. You can type in your questions in that questions window that's pointed by the big arrow on that slide there. And we want to keep it as interactive as possible. So, any questions, if something's not clear on what Uday is showing, please type in your questions and we'll try to get to it. We'll either answer it. I will be watching for the questions in the background. We'll either get to it right away, or we'll have Uday show that if it is not clear. And then we typically, if time permits, we also allow the last 10 minutes for questions, but usually what's been happening is we typically run overtime, and these 10 minutes never seem to happen, it seems like. In any case, we like to keep it very interactive, so please feel free to put your questions into the questions window. Next slide, please, Uday. Okay, so today's topic, as mentioned, is Advanced 3-Axis Machining, and the other highlights of the webinar would be reroughing. We'll be talking about reroughing, 3-axis reroughing. Also be talking about radial and spiral machining in the 3-axis mode. Flat area machining allows you to clear flat areas, not only roughing as well as finishing. And then constant 3D step-over machining as well. Some of the typical cases, use cases for this toolpath method. We'll also be talking about remachining methods, where you can come in with a smaller tool or even a large tool to do remachining after you've done the roughing. Methods like pencil tracing and valley remachining. And then for fine control machining, we'll also be talking about curve-based machining. You can use between two curves and curves projection. So quite a few things to cover today. So without any further delay, I'll let Uday take over. It's all yours today.
Thank you, Joe. Hello, everyone, and thank you again for joining us for today's webinar, a part of our AMS webinar series. And we will be covering several of the advanced 3-axis topics today in our webinar. And we will be covering this both in our VisualCAD and also we'll touch upon in our standalone flagship VisualCAD.CAM product as well. In our previous webinar, we covered 3-axis methods like horizontal roughing, which is also known as Z-level roughing, and also we talked about a couple of different types of finishing methods. Today, we will be focusing more on some of the advanced 3-axis methods. So the part that you see here is a cavity for a mold, and you'll notice that I've already programmed a roughing operation. I'm not going to get into a lot of details in the roughing, as this has been covered in our previous webinar. So we have a horizontal roughing, or also known as a Z-level roughing toolpath, that's programmed on this cavity. And I'm going to go ahead and quickly run a cut material simulation for the horizontal roughing operation, so we can take a look at how we can program some of the advanced 3-axis methods like re-roughing. So the roughing operation that we programmed here with a larger cutter, in this example, we're using a 1/2 inch end mill, is unable to clear out areas in some of the tighter corners in here and has left more material. So in order to be able to go back and clear some of the materials in these areas, we would like to go back and rough it out again, taking into account the stock that has already been left from the previous process. So if you notice here, there's materials being left here because these corners are really tight, and the cutter is also not able to get into some of these lower areas in here. So we could go back and rough it again, and taking into account what is called the in-process stock, which means the stock that's being left from the previous roughing process. And this can be programmed using a method called horizontal re-roughing. And this can be found under the 3-axis advanced methods. You'll find horizontal re-roughing. So a couple of things to
there was a question that as you're talking about these methods, if you can mention in what configuration that they are available, that'll be good.
I will certainly do. Thank you. So the horizontal re-roughing is available in Pro and Premium configurations of our mill module. So the horizontal re-roughing takes into account the in-process stock, or the stock that's being left from the previous step to create the roughing operation. So rough it out again, looking at the stock from the previous step. So the parameters for this operation are very similar to what you've seen in your roughing operation. You could select regions for containment if you'd like to contain the toolpath to a specific area, or you can skip the containment selection, pick a tool. So typically you would want to pick a tool that's smaller than what was used in the previous operation. So in the roughing operation, we used a 1/2 inch end mill. So for the re-roughing, I'm going to select a 1/4 inch end mill. Set feeds and speeds, specify clearance, and then in the cutting parameters, you typically want to leave a little bit of less amount of stock than what you left in the previous roughing operation. So I'm going to set the stock to leave to 10 thousandths. Specify cut levels. You can specify it as a percent tool diameter, distance, or number of levels. Set your engage and retract parameters, and also to fit arcs to tool paths as a recommended. Set the arc fitting tolerance to be 2 times of what you specify as your in tall and the out tall and the global parameters. So we'll now pick generate. In this particular process, the horizontal re-roughing toolpath is being computed, so it takes into account the stock that's being left from the previous steps. If I'm going to display the toolpath visibility here, you will notice that it's cutting areas where the previous cutter was unable to get in. So you can go back and notice in the toolpath display here, in this case, it's also cutting these holes. So I'm going to exclude the holes from being machined. So I'm going to pick a region for containment, and I'll select, I can pick either curves or face edges. I'm going to pick this curve to contain the toolpath. And if you'd like to make any changes, you can make changes to your step over or step downs, and then generate the toolpath. So we are only roughing out inside the cavity area. We have the toolpath in levels. As you can see, it's removing material that was uncut from the previous roughing operation. And there's our toolpath display in levels for re-roughing. Now let's go ahead and run a cut material simulation. So we'll switch to the simulate tab and select play to run the simulation. So we had left 25,000 stock in the roughing operations, and the re-roughing operation, we're taking it down to 10,000 stock. And you can always select pause and then pick simulate to end to run through the simulation. So we have the roughing operation, the first step. The next step, we're doing a re-roughing operation where we are bringing it more closer to the net shape of the part to make it easier for your finishing process. So you could run multiple iterations of re-roughing. So I could go ahead and re-rough it out again with a smaller tool if you need to rough it out again. So the in-process stock is taken into account in the re-roughing operation, and the parameters that you see in the re-roughing operation are very similar or exactly the same as what you have the controls for your cut pattern, step over, cut levels as you see in the roughing operation. Again, this re-roughing method is available to you in Pro and Premium configurations of our mill module. Now, once we have performed the re-roughing operation in here, you'll notice that there are some areas that are flats on the model that haven't been fully machined or cleared out. So to program these flats, there's a couple of ways you could do it. One is you can use the option to select clear flats under cut levels in roughing, or with the advanced 3-axis methods, we have a finishing method called clear flats machining. So you can use clear flats machining, and you can specify a region for containment. Select a tool. So I'm going to use the same 1/4" end mill to go back and clean up these flats. Specify feeds and speeds and clearance. So I'm going to skip through getting into details about feeds and speeds and clearance, as we've already covered this in our previous webinars. Specifying the cut parameters, where you can set your tolerances, your stock to leave. So if you want to finish it to the floor, finish it to the flat of a flat face, you can set the stock to leave to 0. You can choose your cut pattern, your cut directions, your step over. You could also specify Z containment. So in this case, I don't want it to machine the top face. I could specify stay away from the top face by a small value. I can put in like -10 thousandths. Specify engage and retract parameters, and advanced cut parameters can be set. And then selecting generate will create a toolpath just to clean up each of these flats. Let me go ahead and display the toolpath in here, and you'll notice that the clear flats machining automatically identifies the flats from your 3D geometry and creates a flat area machining toolpath to clean it out. Again, the clear flat tops machining is available as part of our advanced 3-axis methods, which is included in Pro and Premium configurations of our mill module. So let's go ahead and run a simulation for the clear flats machining. And it's, as you can see here, it clears out the stock that was left on these flat faces with the clear flat machining. So we have the roughing operation program, the re-roughing, and then the clear flat tops to finish off these flat faces. So in the next step, we are now ready to get to some of the finishing operations. We've already covered a couple of finishing operations in our previous webinar, which was parallel finishing, where parallel finishing can be used as both pre-finishing and finishing operations. So in this particular case, I have a parallel finishing operation generated as a pre-finishing operation, and I could specify to leave some stock in here. So I'm going to leave about 10,000 stock to create a pre-finishing pass. And with the parallel finishing, you'll notice that the cutter follows with in an XY pattern, like rastering back and forth, following the 3D geometry. So with the nature of parallel finishing, you might end up seeing scallops being left in these steep sections depending on your angle of cut that you specify in the operation. So for parts or for features like these, we have other advanced or other type of 3-axis toolpath methods that we can apply to generate the toolpath. So we've also looked at parallel and horizontal finishing in our past webinar, which would be horizontal finishing would be more like a Z-level finishing operation in here, which works great when you have steep sections to clean up the steep areas in the model. You can always refer back to our past webinar to learn more about parallel and horizontal finishing. Horizontal finishing does the steep sections in here. Now today we're going to learn about some of the other types of 3-axis methods that are available to you. The first thing I'm going to be covering here is radial machining. Now the radial machining method is available starting with our standard configuration. So standard, expert, pro, and premium configurations of our mill module include radial machining. So I'm going to choose radial machining. Now this radial machining is a method that can be used for either as a finishing or a pre-finishing operation that can be used with areas that have a circular or a near circular characteristics on a model. So in this case, you see the cavity on the model here. which can be used. It's a near circular feature. We can use this as a, we can pick a containment region to machine these pocket bottoms using radial machining. So for this, I'm going to use a containment region, which could be by selecting curve edge regions, and I'm going to pick either a curve or I can select a bunch of surface edges. So I have this region selected for radial machining. For the tool, I'm going to be picking a 1/4 inch ball mill. We'll set feeds and speeds and clearance. So clearance is set to automatic. In the cutting parameters, you could specify your tolerances in stock, very similar to other finishing methods we've talked about, parallel finishing and horizontal. In the cut patterns, the cut traversal can be set to zigzag or zig. So selecting zigzag will cut in both directions. Zig would be cutting just in one direction, either from the center towards the outside edge or from the outside towards the center, depending on how you specify the start point. You can also control the cut direction, either to be climb or conventional, and specify the step over. So I'm going to go ahead and generate this toolpath in here, and then we'll take a look at the toolpath and go over it. So the radial toolpath is being generated here, and you can see it starts from the center, work its way out towards the edge of the boundary region that you selected. And since the cut pattern is set to zigzag, it's going to traverse back and forth as it follows around the part. So this is a finishing method that you can use for regions that have circular or near circular characteristics and can be used for both core and cavity molds. So I'm going to switch to the Simulate tab and select Play to run the cut material simulation. And you can see the radial finishing cut pattern. You can toggle the visibility of your toolpath during simulation as well. So the cut can be set to either climb or conventional. Again, this radial finishing method is available in configurations right from standard all the way up to premium. So I'm going to choose pause to pause the simulation, and then pick simulate to end to run through the simulation. Once the simulation is complete, we'll go back and take a look at some of the parameters we talked about in radial machining. So your cut direction can be set to climb or conventional. So toggling between climb and conventional reverses the direction of cut. The cut traversal can be set between zig and zigzag, and the start point can be set to inside or outside. So selecting inside will start at the center, work its way towards the outside. Picking outside will start from the outside, working its way in. Now you can also choose to leave a minimum radius. So if you don't want it to go all the way out to the center, you can specify a minimum radius to leave. So for example, I could set leave 100 thousandths out of the center, or you can even specify, you can pick the center point as well. And then when you generate the toolpath, it's going to stay away 100 thousandths off from the center. So since you have already machined the flat, if you want to keep it away from machining the flat area, you can specify the minimum radius to be left in here. And then generating the toolpath will exclude that region from being machined. So radial finishing is one of the additional ways for finishing that can be applied in 3-axis toolpath methods, available in configuration starting with standard and above. The next method we're going to be covering here is going to be spiral machining. And this method is also available in configurations starting with standard and above. So standard, expert, pro, and premium configuration offers spiral machining. Again, the spiral machining is a method of generating spiral toolpaths. This can also be used effectively for machining circular regions, which can be used in both core and cavities. So it could be used working with when you have convex or concave or convex shaped geometries. You can use spiral machining. You can specify a region for your containment. We'll pick the tool. In this case, I'm still going to be using the same 1/4 inch end mill. we'll skip through feeds and speeds and clearance and then dive directly into the cut parameters. You can specify a cut direction. This could be set to climb or conventional. And the start point could be starting from the inside. You can start the spiral from the inside, which happens to be in this case to the center, and working its way towards the outside. So with the spiral machining, there's just going to be one entry and one exit as it creates one continuous spiral toolpath. And you also have the option to specify to leave a minimum radius. We'll set the step over in here and then generate the toolpath. So it creates a spiral toolpath, and the toolpath is projected down to the underlying 3D geometry. Now the spiral machining works great when you have areas that are not too steep. I'm going to show you an example of what would happen when you pick some steep sections on the model using this particular part as an example. So let's go ahead and take a look at the toolpath. So there's the spiral, it starts in the center, creates one continuous toolpath. So there's just one entry move here and then the final exit. So there's no retracts or no transfer of, the cutter lifting up and moving over, as you're basically cutting it, creates one continuous spiral path. So this is also a very nice way of finishing circular features on the part.
I should also add, Uday, that the center of that spiral can actually be moved around. There's a way you can actually specify the coordinates of the center point. That was a question. So,
thank you, Joe. Yeah, absolutely. You're absolutely right. So like how we can set the center point for the radial machining, we could also do the same for spiral machining as well. I'm going to skip through the simulation and then we'll just touch upon the topic. So we could specify the center. So if I want it to be off-centered, I can use specify, pick a point, and I can just go snap to a point. So let's say I want to pick this point right here. So it's going to use this as a center for the spiral path, and you'll notice that the toolpath gets automatically shifted, and it uses this as the center of the spiral. If you do not specify a center point, it automatically determines a center based on the part region that you chose as your containment, so it uses the center of the part region. You could also specify the minimum radius to be left in here, exactly how we did in the radial machining, so you can specify to leave a minimum radius as well. Now, what would happen if you had some steep sections as part of our containment region selected? So I'm going to drop this area and then go back and pick the outermost region in here. So when you have a lot of steep sections, it's going to start riding along those areas. So spiral machining is not ideal when you have a lot of steep sections in here. As you can see, it leaves out, it looks more, the tool paths are much spaced further apart, even though it's maintaining a uniform XY step over. As it gets projected to the part geometry, you end up leaving, you're going to end up more scalloping in here. So it's ideal that you use spiral machining for sections that are not too steep. You can exclude those sections by using containment regions, either by offsetting this outside region away from the steep sections, or by selecting a smaller containment region. And then you can apply different types of finishing techniques for the steep sections, like horizontal or Z-level finishing, which we covered in our previous webinar. So there's our spiral machining toolpath. I'm just going to run through the simulation again. You can skip through it by selecting pause and then simulate to end. Okay, now that we programmed a few different types of finishing methods in here, you'll notice that there is still some scalloping being left in the simulated part on the machine part, as you can see right here, based on these different types of finishing methods we've generated. So we'll touch upon some of the additional finishing methods where how we can go back and effectively clean up some of those areas as well. And one of the methods that I would like to cover here is a method called constant 3D step over pocketing, or also known as constant scallop machining. Now this method is available in Pro and Premium configurations of our mill module. So under the 3-axis advanced menu, you'll find a method called 3D offset pocketing. This is also known as constant 3D step over machining or constant scallop machining, where it maintains a uniform 3D step over and is a great way of programming areas that are both steep and not too steep areas. So for example, this method also requires you to select a region, which is called a part region for machining. So you could select curves, or you could select face edges. So in this particular example, I'm going to pick this curve that's on the edge of this pocket boundary here. We'll use that as our part region. The tool, you could use the same ball mill. Typically, you would recommend using a radius tool like a ball mill or a corner radius tool for finishing using 3D offset pocketing or any of the 3D finishing methods. You could specify your cut conditions in the cut parameters tab, where you can specify your cut control, whether you want to climb, conventional, or mixed. For your cut direction, the pocket start point, you could either start from the inside or outside. So in this particular case, I'm going to start the cut from the outside of this cavity. So it'll start from the outer edge and work my way in towards the part. And we could control the step over. So I'll use a 20% step over and then pick generate. Now this toolpath method, as mentioned, it generates a constant 3D step over, or known as uniform 3D step over, also known as constant scallop machining. So when you have steep sections and flat or near, shallow areas, or I would say freeform or sculpted bottoms, it maintains a constant 3D step over. So the time for this toolpath method to generate is going to be, you'll notice that it's going to be slightly longer than some of the other methods that you've noticed. Either could be parallel finishing, radial, or spiral machining, as it creates a uniform 3D step over. And you can see that the step over remains uniform for both steep sections and also for near flat sections. So this is available as part of the advanced 3-axis methods, and it's included in Pro and Premium configurations of our mill module. It's called 3D offset pocketing, also known as constant 3D step over or constant scallop machining. Now in this particular example, I chose the start to be on the outside, the pocket start point. I can switch this from outside to inside, so the cut path will start from the inside, work its way towards the outer edge. So I'm regenerating the toolpath with the change I've just made. And you can notice that the toolpath, once it's generated, will maintain a nice uniform step over. So it's a great way for finishing, not just mold cavities. You can also use them for mold cores. We'll cover that in another example as we progress along this webinar today. So you'll notice that the cutter starts from the inside, works its way towards the outer boundary. So I'm going to run the simulation here, and this maintains a uniform constant 3D step over. So at any time during the simulation, if you want to run through it, you can select pause to pause the simulation, and then pick simulate to end, and you'll notice that the progress bar shows the simulation running all the way to the end of the process. So results in a nice finish. This can be used both as either a pre-finishing or a finishing operation, the 3D offset pocketing operation. Okay, so now that we have covered some of the advanced 3-axis pre-finishing and finishing methods, we'll focus on a couple of remachining or refinishing methods. One of them I'm going to cover here is going to be called pencil tracing. Now, pencil tracing is a great way to machine areas where the bitangencies on this part, as you can see, where you have a vertical and a flat surface, or where the tool is in contact with two sides of the surface for cleaning up those areas, you're going to be typically using like either a radius tool like a ball and mill, and the cutter is going to be following a path where two or more sides of the cutter are in simultaneous contact with the part. So it basically allows you to go back and clean up these areas, and the system automatically identifies those bitangencies for generating the toolpath. And I'm going to demonstrate that by creating a pencil tracing toolpath. Now, this pencil tracing toolpath method is available in Pro and Premium configuration. It comes included with it, and it's part of our advanced 3-axis machining package. The pencil tracing is offered in both Pro and Premium configurations. Again, you can select regions to contain your toolpath if you'd like to. In this case, it's not necessary to pick a region. We can generate a toolpath. I'll pick a tool in here. I'm going to start with a larger cutter to go back and just clean it up in here. In the pencil tracing, you can specify your direction for cut. So I'll just leave it as climb and then pick generate. So system automatically identifies those bitangencies on the part and creates a path to go and clean it up. So you can see both it cleans up not only the shallow and the steep sections on the model with a pencil tracing toolpath. So this is a great way to finish areas where you notice these scallopings that are being left from the previous cut, previous finishing operations. And with the pencil tracing, you can also use multiple passes if necessary, where you can generate multiple cuts. So you have these controls in pencil tracing where you can choose to do multiple cuts, and you can do one additional cut on each side of the pencil trace, or you could do 2 on each side. You also have advanced parameters where you can split the cuts for flat and steep sections, and you have these controls that are available in the pencil tracing operation. So pencil tracing operation is a great way to go back and refinish and clean up these areas where you notice scallops, and the system automatically identifies those bitangencies, from your part geometry to clean up those areas. Folks, if you do have any questions, you're welcome to post those questions in the questions panel, and we'll try to get those questions answered for you. The next method that we'll be focusing as part of our remachining is called valley machining, or also known as valley remachining. Now, this method is offered in both Pro and Premium configurations of our mill module. It's called valley machining, or also known as valley remachining. In this particular method, we'll typically go back and refinish with a smaller tool. In this case, it could be a 1/4 inch, or even a smaller, it could be like an 1/8 inch cutter. And in the cut control, you would specify the reference diameter of the previous tool that was used. So if you used a 1/2 inch or a 3/8 inch cutter, you could specify that as your reference tool diameter. So as you can see here, the refinishing is the areas that were uncut or needs to be refinished based on a reference diameter is identified, and you're going to be using a smaller tool to go back and clean it up. In the cutting parameters, you can specify your cut pattern, your step overs, and if you need to split the cuts, you can split the cuts for steep and flat sections. So I'm going to use along cuts for both flat and steep, and then generate the toolpath. So this is creating, again, it identifies the bitangencies, and based on the reference tool diameter, it's going to go back and recut those areas with a remachining toolpath to clean up those areas that couldn't be finished using your finishing process where the scallops were being left. So valley machining.
Just a quick explanation on the term bitangencies. When Uday says bitangencies, what we mean is where the tool is actually touching on both sides. So it either could be touching on either side of the cutter, or it could be touching on one area at the bottom of the cutter on the other side, maybe to the left or to the right. So we detect those areas where the cutter is actually, making contact with the part surfaces, in multiple places and then generate the toolpath. So that's what we call bitangent toolpaths. Thank you.
Thank you, Joe. So if I swap this out to a smaller tool, you're going to get more number of passes in here because the reference tool diameter was set to 1/2 inch. So this is also one of the nice ways to go back and refinish and get a really nice finish in those corners around, or fillet sections, or fillets or radiuses that you have on the mold. So less amount of manual work, cleanup work that would be involved, and especially when you're cutting metal, this is going to help you go a long way to get you a perfect finish that you need on a model. So now that we've covered some of these refinishing methods, we'll take a look at a few other examples on how these can be applied on other molds, cavities, or core models. So I'm going to go ahead and switch to another example here. This is a core model for a camera body, as you can see right here. We have already programmed a few operations, and I'll try to go through them. So we have the horizontal roughing operation program, which is the roughing in levels, or also known as Z-level roughing. And then we talked about clear flats, and we'll see how this clear flats would be helpful in this particular case here. As you can see, the model you have a drafted wall here. The camera body has a draft on it. So the clear flat machining automatically identifies these flat sections on the part to clean it up. So you don't have to go ahead and create additional regions to program like 2-axis operations. So you can take advantage of the clear flat tops in your advanced 3-axis machining method to automatically identify these flat areas to machine them. And you can use a flat mill to mill these flat sections. Now we programmed re-roughing operations on this part. We have programmed multiple re-roughing operations. The first one is with a 1/4 inch end mill, and the next one is with a 1/8 inch end mill. So you can have multiple iterations of re-roughing to bring it as close as possible to the net shape of your part. So it makes it easier for your finishing process, as you'll have less amount of material that needs to be removed, and also reduces tool wear as you go through your finishing process.
Well, there was a question about pencil tracing toolpaths, smoothing, and also the same thing in valley remachining. I can talk a little bit, and then you can add your thoughts as well. As I mentioned, the pencil tracing and valley remachining methods use bitangent contacts. So by nature, we are detecting bitangent contacts, and in some cases, these are more than 2 contacts in some situations, except if you're cutting a fillet, for instance, with a cutter of the same radius. It is really a very difficult mathematical problem for us, because you're going to have very many places where the cutter is contacting the fillet. And so those kind of situations, you're going to run into jagged toolpaths, because the toolpath that's the machining algorithm is thinking, oh, the cutter is touching in multiple places, and then it moves to a different location, and it's not cutting or not touching in so many places, or maybe not touching at all, as in the case of a very variable radius fillet. So those are things you need to keep in mind when you're using this pencil tracing and valley remachining methods. So typically we find users who use the same radius cutter on a fillet. When they try to machine using the same radius of a fillet, you're going to see a lot of jagged cuts. So what we would suggest is use a larger cutter, so to remove some of these multiple contacts, and only getting clean by contacts. So that would be one way you can remove these jagged toolpaths. The other one would be obviously tightening the tolerance. That would help as well, because you're introducing more precision in the toolpath methods. So those are the few things that I can think of. Maybe they can add a few more.
Joe, I totally agree absolutely what you said. And also one of the things that I could see is if the radius of the tool is in close proximity with the radius of the fillet on a part, one of the techniques users can look into using is a method called curve machining, so curve projection machining. So they can actually pick a curve where we have at the base edge of the fillet, we can select the curve and then drive it with a curve machining or a curve projection machining toolpath as well. So in this particular example, I just chose these curve edges on the model, and we can select a small tool or a tool that matches this radius or close enough to the radius, and use a curve machining and specify the cut type to be along curve. So that'll basically, eliminate some of those jaggedness in the toolpath with the curve machining, because the curve is being projected to the underlying model, and the cutter path follows the curve or stays on the curve as you're trying to clean it up. And also I would avoid using any flat end mills or square end mills for pencil tracing of these operations. As Joe pointed out, you're going to end up running into these jaggedness on the toolpath. So try to use a radius tool, which could be either a corner radius tool, a flat mill with a slight corner radius, or use typically a ball mill cutter for pencil tracing and remachining toolpaths. Now, talking about curve machining, we have two different types of curve machining methods. One is called the curve machining, or also known as a curve projection machining. I apologize, I forgot to cover this as we were talking about this part, but I'm going to go back and revisit this right now. So curve machining or curve projection machining can be used to machine along curves, and the curves are automatically projected to the underlying 3D model. So you could select one or more curves, which could be open or closed, and you can apply this 3-axis curve machining method. Again, this method is offered in both Pro and Premium configurations of our mill module. This is part of our advanced 3-axis machining solution. So you can use curve machining, and in this particular example, you can see that I've chosen the chain of open edges at where the fillet ends and the cavity here, and I've chosen a tool. I've chosen an 1/8" end mill. I can switch this to a 1/4" tool, and if the cutter is too big and the fillet, you can see it automatically rides along the side walls, and it's not going to gouge into the part. So it honors the tool geometry and checks against the tool geometry as you're programming the curve machining toolpath. You could also specify to use multiple paths in the curve machining, where you can say cut along and specify to cut both sides by specifying a cutting bandwidth in here, and control your step over. So it's going to cut on both sides of the curve. And as you have these steep sections, you can see it's going to ride along these. In this case, the radius is too close to the radius of the model, and you can see some of these jaggedness in the toolpath. So you may want to make sure that you specify a small enough tool and control the radius in here, and specify how far you want it to specify the cut bandwidth to step over to clean it up. So this would be curve machining toolpath, which can be used again as a toolpath method to go clean it up, clean up certain areas in a certain cut pattern that you want to use, and you can drive the cutter on the curve following the curve pattern. Now, there's one other method that I would like to cover here, is called the between curve machining, which is available in Pro and Premium configurations of our mill module. You'll find it under the advanced 3-axis methods, between two curves. So in this case, we would have to select two curves, as the name suggests, between two curves. The two curves can either be two closed curves or two open curves. You can't mix and match. You can't pick a closed and an open curve. So you either have to select two closed curves, or you pick two open curves. So if I pick these two as two open curves, I can select these two and then specify a tool for it. In the cutting parameters, I could choose the cut direction to be along, so the toolpath will flow along the curve, and you can control the step over as well as your cut pattern. So selecting generate will generate a between two curve finishing, and the toolpath starts from the first curve that you chose, which is going to be the curve on the top right here, and it flows to the curve at the bottom. So it kind of morphs between the two curves following the 3D geometry. So this is a method that you can use for cleaning up either steep sections or shallow sections. Between two curve machining is also a good way to finish up steep sections, especially on a part like this, where your parallel finishing or other methods is not going to give you a great finish on the steep sections. You could use between two curve finishing. Now, there's a couple of things I would like to point out in between two curve finishing. If you're working with closed curves, you need to make sure that the curves that you're selecting are also flowing in the same direction. So in this particular case, if I select these chain of edges and generate the toolpath, you will notice that if the curves are not flowing in the same direction, you may not get the desired result on the toolpath, because you'll see here that the toolpaths are kind of getting twisted over and not following, the curves are not in the same direction. So you need to make sure, if you're selecting curve regions, you want to make sure that the curves, both the curves that you select, are flowing in the same direction and also have the same start points in the close proximity to one another. So I'm going to generate this toolpath, and I'll show you how you can set the curve direction and the start points. For folks who are using Rhino, you can set the direction of the curve by going into Analyze Direction, and you can select the objects. Here I can select the two curve geometries and determine the direction. As you can see, the two curves in here are both flowing in the same direction. So if you need to reverse the direction, there's a command called flip to flip the direction. If you just need to flip the direction of one of the curves, you just click on the curve and it'll flip the direction for you. If you want to flip the direction for all the curves, you can use flip all. Now to change the start point, you can use the command called curve seam. That's under curve edit tools, adjust curve seam, and you can pick the curve and you can drag the start point over anywhere along the curve. So you want to make sure that the start point lines up close to one another. If I select these two curves and select curve seam, it'll show you where the start point is. And you want to make sure start points are lining up close to one another. And when you generate the between curve machining toolpath, it flows between the two curves, and you want to make sure that the direction of the curve and the start point are lining up. Now you could also use the predefined regions to control your start point and the direction as well, if you prefer to use the predefined regions as your machining regions. So the curve machining and between two curve machining are curve-based machining methods where the toolpath uses the curve to follow the pattern, but it's again honoring the 3D geometry, following along the 3D geometry. So these are some of the techniques that you can use for finishing up specific areas, and you can drive the cutter the way you want it on the 3D geometry. Again, these methods, the curve machining and between two curve finishing, are available in both Pro and Premium configurations of our mill module. So going back to the camera body core model that we were working on earlier, we talked about roughing and re-roughing. The re-roughing operation was done in multiple iterations in here. We have parallel finishing that we are using as a pre-finishing toolpath, and then followed up with the 3D offset pocketing, or also known as constant 3D step over machining. So you'll notice here on the steep section how nicely the 3D offset pocketing maintains a uniform 3D step over the parallel finishing that you generated based on the cut, the direction, the angle of cut was set to 0, which follows along the x-axis, rastering back and forth. So it kind of leaves a larger scallop in here on these vertical sections. So with cleaning up with the 3D offset pocketing will result in a much finer finish, both on the steep sections as well as the sculpted sections. Also, I would like to point out here is we've capped or we patched some of these features in the mold, the core mold, so that the cutter nicely transitions and not diving into these features. So you can actually create surfaces like a pat surface, or you can basically mask these cavity, in the geometry and then you can place them on different layers in your CAD. So in this particular case, we've actually masked them. So you can see there's like these cavity pockets in here on the camera body, which we've created surfaces to mask or cap them. So when you generate your roughing and finishing toolpaths, and if you have these surfaces visible, the cutter will not dive into those pocket or cavity. So you can use them for programming your roughing and finishing toolpath. And finally, you can go ahead and expose those areas by hiding those surfaces to generate your finishing toolpaths, or you can even do a combination of both 2 and 3 axis toolpath to finish off those pockets in there. Or if you'd like to do a pencil tracing operation to go back and clean up, you can see this pocket has a draft on it, so the pencil tracing will be able to identify those bitangencies to clean up to result in a nice finish. Again, in this particular case, we are using a radius cutter, like a 16th inch ball mill cutter, to go and clean it up. So here's an example of how you can program a core mold using different advanced 3D toolpath methods with a combination of re-roughing, 3D offset pocketing, pencil tracing, and also you can combine it with 2-axis toolpath methods. Now I would like to go through an example of a cavity of the camera body that I've programmed using our VisualCAD.CAM product here. And as you can see, we've started out with a facing operation to remove the stock that's left above the face of the part to bring it down to the thickness of the part, and then followed up with a roughing toolpath, which we have covered in our previous webinar, and then a couple of iterations of re-roughing to bring it as close as possible to the net shape of the part. And then we have added a clear flat tops, which we covered earlier during the webinar, to machine all of the flat faces in the cavity. So it automatically identifies the flat areas, and the clear flat tops can be used for machining the flat areas in the model. So we've generated horizontal finishing, Z-level finishing for the steep section in here, and repeated the same horizontal finishing for the other section of the cavity. For machining flats, for areas that are not perfectly flat, have a certain angle, you can use a method called flats or plateau machining, which is available as part of our advanced 3-axis package, included in both Pro and Premium configurations. It's called flats, or also known as plateau machining, and you can specify to machine areas that are flatter than. So you can say identify areas that are up to 35 degrees of steepness, and you can machine those areas using plateau machining. And in this particular example, we've selected part surfaces. So you can select surfaces are the areas that you'd like to machine, and you can select them as part surfaces instead of having to select part regions. We've selected surfaces, and we've chosen the surface extent condition to on, which means the tool tip will stay to the edge of the surface boundary. So you can select one or more surfaces and generate plateau machining, or also known as flats machining. And we've set the angle limit to be up to 35 degrees. So it automatically limits the toolpaths to areas up to 35 degrees. As you can see here, it is not machining areas that are steeper than 35 degrees. So this can be used to finish as a pre-finish or a finish operation using the plateau machining operation. Now, we talked about spiral machining earlier in the webinar today. You can either select a part region, or in this particular example, I've chosen part surfaces. So you could select one or more surfaces, and I've chosen the surface extent condition in here to 2, which means the cutter will stay completely inside of the surface edge boundary. So you can see it stays completely inside, so it's not touching, riding along these steep walls. The cutter stays completely enclosed or within the surface edge boundaries in here when you set the surface extent condition to 2. And I have an example of the horizontal finishing where we've set the surface extent condition to go past, so it'll go past it so the cutter can get all the way down on the sides to fully clean it up. So the surface extent conditions are available in the 3-axis toolpath methods, where you can pick one or more surfaces and you can choose a surface extent condition to be on, to, or past. So you can select not just part regions, you could also select part surfaces as your control geometry for machining in 3-axis methods. And finally, I have a pencil tracing toolpath that we programmed in here. So that automatically identifies the bitangencies and cleans up these tight corners with the pencil tracing toolpath using a 16th inch ball mill cutter. So you can take advantage of these advanced 3-axis toolpath methods to program complex features and different features on the part to get the desired finish that you need for your mold cores or mold cavities that you're trying to program using our CAM products. I do have one other example in here of a mold core, which I'd like to point out real quick, programmed in VisualCAD.CAM. Similar type of toolpath methods being applied, roughing to start with, horizontal or a Z-level roughing toolpath. Then we have a re-roughing toolpath generated to go back and clean up the areas that were unable to be roughed out using the large cutter. So you can see that the re-roughing brings it more closer to the net shape of your part. And then you have your finishing toolpaths, which could be a 3D offset pocketing, which creates a constant 3D step over or uniform step over. So this can be used for both mold cores and cavities, the 3D offset pocketing method. And you could apply a cleanup pass to go back and identify those bitangencies to clean it up using a pencil tracing toolpath to clean those areas out. So folks, we are close to our hour's time on today's webinar. So if you would have any questions, we'll be more than happy to take a look at that. And also any unanswered questions we have, we will certainly reach out to you via email. We'll try to take a look at it, as we had, looks like we had several questions in the webinar today. We will try to get these unanswered questions. We'll send them an email to you, and we'll send them a response to you via email. So we thank you for joining us today for our webinar today on advanced 3-axis machining. We appreciate your time. Thank you all for joining us today, and have a good day. Thank you.